Now coming to the main topic for this video. The main topic for this video is the first application of Biot-Savart's law, which is the magnetic field intensity, or finding the magnetic field intensity at a point due to an infinite current carrying wire. Now let me tell you, this derivation is very important. That is why I'm only dealing with this derivation in this video. Now I must have used this phrase very important for other derivations also, but this particular derivation is one of the highest ranking in the list of important videos. I cannot emphasize its importance enough. So what my suggestion is, watch this video, understand the derivation clearly, and practice this derivation. The more you practice, the better it is for you. So let's get down to the derivation. So first of all, we have this wire. It's supposed to be infinite in extent. Alright, so this wire is carrying current I, and what we want to do is we want to find the magnetic field intensity at point P due to the whole length of the wire. So we want to find the magnetic field intensity at point P. Say for example, this point P is at a distance A from the wire. So this distance A is fixed. Alright, so in order to find the magnetic field intensity at point P due to the whole wire, first what we need to do is, what Biot-Savart's law tells us is, it tells us first of all we have to find the magnetic field intensity at point P due to a small current element, IDL. Current element is IDL, remember, current multiplied by the elemental length is called current element. DL itself, only DL is called elemental length, don't forget. So Biot-Savart tells us that first of all we want to find the magnetic field intensity at point P due to this elemental length DL. Alright, so according to Biot-Savart's law, the magnetic field intensity at point P due to current I flowing through the elemental length DL is given by this. dB is mu naught by 4 pi IDL sine theta by r squared. Where do we get this from? We get this from Biot-Savart's law. So this is how you start. So this is a DL. Now this elemental length DL is at a distance r from point P. So this angle is theta. The angle between the elemental length DL and the line joining the elemental length to point P, this angle is theta. So of course this is 90 degrees. So this is A, this is R, this is theta, this is a DL. And let us suppose this distance OM, M is the midpoint of your elemental length. So this distance OM, say for example, is L. These kind of small DLs makes up your length L. Don't forget that. So since this is a right angled triangle, so now in right angled triangle, MOP, theta plus phi, I haven't shown phi over here. So phi is this angle. So we are supposing this phi over here. So theta plus phi of course is 90 degrees. So therefore theta can be written to be 90 degrees minus phi. Alright, so which implies that sine theta is sine of 90 degrees minus phi. Now sine 90 minus phi is cos phi. So therefore sine theta is the same as cos phi. Now what are we trying to do over here? Now look at this expression for Biot-Savart's law. Mu naught by 4 pi is a constant. I is certain magnitude of current flowing through the wire. Now DL is a variable. This DL could have different lengths. For different persons, the length of DL could be different. Alright, so DL is different. DL is a variable. Sine theta likewise is a variable because theta is a variable. Why? Since we could have chosen DL to be anywhere along the length of the wire. Along the length of the wire, we could have chosen DL to be anywhere. We could have chosen DL to be over here. Alright, so if DL was here, alright, this angle theta would be different. If DL was here, the angle theta would be different, of course. If DL was somewhere over here, this angle theta would be different. Alright, so therefore theta also is a variable, and for different positions of DL, this value of R would be different. For the same point P, such that A is fixed, remember, for different values, for different positions of DL, theta would be changing, R would be changing, and dl itself could be of different lengths. All right, so dl is a variable, theta is a variable, r is a variable. So since we have three different variables over here, what we are trying to do is we want to express all of these different variables in terms of only one variable. Okay, so instead of dealing with so many variables, if we only have to deal with one variable, that is more convenient for us. So that is exactly what we are trying to do. Okay, the variable that we want to deal with is phi over here. You will see that all of these variables, different variables, can be expressed in terms of one variable, phi. And that is exactly what we're trying to do over here. So from here, we saw that sine theta, this sine theta over here, can be written as cos phi. Okay, so also in triangle MOP, in the same triangle MOP, what we can do is look at tan phi. Tan phi is perpendicular divided by base. So perpendicular has length L. You can see in triangle MOP, the length of the perpendicular is L and base is A. Okay, so tan phi in the same triangle, tan phi is L upon A, or L can be written as A tan phi. Therefore, dl is A sec squared phi d phi. What we are doing is we have this, L is A tan phi. This is what we have. So differentiating with respect to phi. So differentiating with respect to phi, what we get is dl by d phi is equal to A sec squared phi, because the differentiation of tan phi is sec squared phi. And it's like we are cross multiplying. So therefore we get dl is A sec squared phi d phi. Okay, hope you've understood. So therefore this is what we get. dl is A sec squared phi d phi. This is my equation number 3. So again, I see dl can be represented in terms of phi. And finally, the other thing is, in the same triangle, cos phi is A upon R. Okay, let us give a look at the picture. In the same triangle MOP, cos phi is what? Cos is base by hypotenuse. So base is A, hypotenuse is R. So therefore, cos phi is A upon R. So here we can write R is A upon cos phi, which can be rewritten as A sec phi. So you can see R is represented in terms of phi, dl is represented in terms of phi, sine theta is represented in terms of phi. So what we are now going to do is, we are going to substitute for these different terms, for sine theta, for dl, for r, in equation number 1, which is this. Okay, so that is exactly what we do. So when we substitute, we get, from equations 1, 2, 3 and 4, we get dB is mu naught by 4 pi. Okay, now we substitute for, okay, let me show you that equation number 1. Equation number 1 is this. So first of all, so mu naught by 4 pi, I is I. Now dl, what was dl? dl was A sec squared phi d phi. So A sec squared phi d phi. So that is exactly what I've done. So mu naught by 4 pi I A sec squared phi d phi. All right, then sine theta was cos phi, so cos phi, you can see here, divided by r squared. Now r, we found r to be A sec phi. Okay, so r squared will be A squared sec squared phi, so that is exactly what we get. All right, then after, so we see that all of the different variables are expressed in terms of one single variable. Then after, we try to simplify it. So this A and one of the A's, they divide each other, sec squared phi, they divide each other. So what are we left with? We get dB is mu naught by 4 pi I upon A cos phi d phi. So this is the magnitude of the magnetic field intensity at point P, at this point P, due to the elemental length, remember, due to current flowing through the elemental length, dl. So this is the magnitude of the magnetic field intensity. So if this is the magnetic field intensity at point P due to a small elemental length dl, then the magnetic field intensity at point P due to the whole length will be a sum of these kind of small dBs. Okay, which means you've understood it, I know, which means we need to integrate this. All right, so therefore the magnetic field intensity at point P due to a wire of finite extent. Don't forget the heading for this was magnetic field intensity at a point due to an infinite current carrying wire. Okay, now in order to land at infinite current carrying wire, let us first discuss what happens in case of if this wire was of finite extent. All right, so if this wire was of finite extent, then the magnetic field intensity at point P would be B, which of course is integration of these kind of small dBs, so which is mu naught by 4 pi I by A, integration of cos phi d phi. Okay, mu naught by 4 pi I by A being constant, they are taken out of the integral sign. And what are the limits of integration? The limits of integration are minus phi 1 to phi 2. Now let us see why we have these values of the limits of integration. Let us also see why one is negative, the other is positive. Okay, so let us look at this picture. So say for example this is a finite wire, this is a point P, all right. Now what we've done is we are measuring, so this is like your angle phi, this is your angle phi, you can see in the picture this is your angle phi. All right, so what we are doing is we are measuring angle phi with respect to this line. So when we measure angle phi in the downward direction, that is in the anti-clockwise sense, when we measure phi in the anti-clockwise sense, we are taking the angle to be negative. And see, since DL could have been anywhere, so when DL is on the lower side of point O, when DL is on the lower side of point O, we have to measure the angle phi in the anti-clockwise sense. So whenever we measure angle in the anti-clockwise sense, we are taking it to be negative. All right. Whereas if we had DL in the upper side of point P of point O, of course, okay, we would have to measure the angle phi. So in that case, this would be angle phi. All right. Now angle phi, if DL is on the upper side, we have to measure angle phi in the clockwise sense. So whenever we measure the angle in the clockwise sense, we are taking it to be positive. So that's the sign convention for the angles we stick to. Okay, if we measure angle in the anti-clockwise sense, that is on the lower side, we take the angle to be negative. Whenever we measure angle in the clockwise sense, that is on the upper side, we take the angle to be positive. So that is about the sign of the angles. Now let's see why one is phi 1 and why the other one is phi 2. Now when we are discussing a wire of finite extent, this point P could have been anywhere. Okay, could have been anywhere in the sense that it is not necessary that this point P lies on the perpendicular bisector of the wire, like in this case. So since point P is closer to the upper end, point P can be anywhere, so it will make different angles with the ends of the wire, as you can see. So when we take DL, so since we are adding the magnetic field due to small DLs could be anywhere. All right, so we measure the magnetic field intensity at point P due to a DL over here. Then we measure magnetic field intensity due to a DL over here. For every DL, the value of phi is different. The value of the angle phi is different. Okay, so when we consider DLs at the ends of the wires, all right, so the maximum value of the angle phi, okay, on the lower side is, we are taking it to be phi 1. This is phi 1. And the maximum value of the angle phi on the upper side, we are taking it to be phi 2. So after understanding the values of the limits of integration, let us proceed further. Let us do the integration now. So B is mu naught by 4 pi I by A. The integration of cos phi is sin phi, and we have the limits of integration. So B is mu naught by 4 pi I by A. We substitute the value, upper value first, so sin phi 2, minus always the lower value, sine of minus phi 1. Okay, so this will give us mu naught by 4 pi I by A sine phi 2 minus of sine of minus theta is minus sine theta. Okay, so that minus sign and this minus sign becomes positive, so sine phi 1. So B is mu naught by 4 pi I by A sine phi 1 plus sine phi 2. So if the question is like find the magnetic field intensity at point P due to a finite wire carrying current, you'll stop over here. This is where you stop. Okay, but since this derivation says magnetic field intensity due to an infinite wire, so if the wire is of infinite extent, then both phi 1 and phi 2 will be pi by 2. Now why is that so? That is because if the wire was of infinite extent, this dl on the lower side would be at infinity. Okay, would not be somewhere over here, it would be at infinity, out of the frame. Okay, so also this dl would be at infinity. So this length r, okay, this length r would be parallel to the wire on both the sides, on the upper side also, on the lower side also. The length r would be parallel to this wire. Why parallel? Because this length r would meet dl only at infinity. Okay, it's like the optimistic definition of parallel lines. So what are parallel lines? Two lines are said to be parallel if they meet at infinity. All right, so therefore this r, I repeat, would meet dl only at infinity on both the sides, in which case the value of the angle phi, the value of the angle phi on both the sides would be what? Would be this angle, which is equal to pi by 2, that is 90 degrees. Okay, so that is exactly what I've written. If the wire is of infinite extent, phi 1 is equal to phi 2, which is pi by 2. Therefore, magnetic field intensity at point P due to a wire of infinite extent is given by B mu naught by 4 pi I by A. We substitute the value of phi 1 and phi 2, which is pi by 2. Thereby we get this. Now sine pi by 2 has value 1. Okay, so 1 plus 1 gives us 2. That 2 and this 4, they divide each other, giving us B is mu naught I by 2 pi A. So this is the value of the magnetic field intensity at point P due to a wire of infinite extent.